All right, so welcome to this open lecture on applied machine learning. My name is Stefan Forsström. I'm an associate professor here at Mid-Sweden University. And today we're going to have a lecture on sort of an introduction, a crash course for applied machine learning aimed towards engineers. So, and if you have any questions for me during my presentation, we will take them in the end. But if you want to ask the question, write them down, you can go into menti.com on the code that you see here on the screen, 7629 9653, and then you can write your questions there for me. All right, so who's the intended target group for this presentation then? Well, my idea is that this presentation will be for people who can code, basically people who at least have some basic knowledge in programming, but perhaps haven't really tried to explore the area of applied machine learning yet, or that they haven't sort of found the time, or sort of just want to get a little bit of a start into exploring this quite complex area actually. So my intention with this lecture is that I will give you a crash course in the fundamentals of applied machine learning. We will have a look at the most popular coding tools that is used for this today, and we will try to solve a quite simple machine learning problem with this. I will show you some code and we will go through it basically. But I will focus on the basics because the intention of this is to perhaps enable you to study this further later yourself. So any mathematics and stuff like that, I will sort of leave out of this scope. So we will just focus on the engineering parts, the coding, and stuff like that. And this lecture, the first lecture of a course on applied machine learning that we will start now in 2 weeks. So if you're interested in learning more, I will talk about that in the end. So this is also like the first lecture of that course. All right, so let's give some background to the whole area. So the general sort of technology development of the last decade has led to an explosion of the available data that we have. We have all of these Internet of Things devices, smart devices, sensors and stuff like that connected everywhere around us. And these are creating a lot of data inside of them. They are sensing the environment, they are knowing what we are doing, and we are being collected data from us, what we are doing on the internet all the time and stuff like that. So with all of this new data, we should be able to do very new and advanced and fancy things, right? And so powered by these devices and the information that they possess. So with this available data, we should be able to create these context-aware services, smart services, artificial intelligence, all of these type of new smart services. But the problem so far has been that the technology haven't really been able to deliver on these expectations. But let's have a little bit of a look back in history. So in the machine learning or artificial intelligence landscape, we have had this domain has gone up and down in interest and expectations during the year. Here on the picture, like in the 1960s, they were very much hyped up about AI. But then in the 1970s, the technology couldn't deliver what was promised. So it really went down in a slope. And then it sort of went back up again during the 80s, 90s. And then again, disappointing results, couldn't really deliver. And then now, when we are sort of here, hopefully we have reached some sort of slope of equilibrium here, so that we are sort of the technology can maybe also deliver on these promises of AI. So let's ask ourselves then, why now? Why 2023? Why now the latest years? Why has AI, machine learning become so big? I mean, one of the biggest reasons is, of course, the hardware maturity. I mean, Moore's law and everything has really pushed us to where we are today with a lot of big and good computing power. I mean, we have small computers in our pockets working around with us everywhere. So a lot of things that happen in the hardware world. And then a lot of things has also happened with the tools, the programming tools, the code, and it has become very much better actually. The availability of it, the simplicity. Previously, you had to have a PhD in mathematics and computer science to even understand and do something with this. But now it's quite easy. You can actually start using it get into it quite easy. So that is sort of why now. this has happened. And what was the problem then? Well, if we look back at the traditional programming or of artificial intelligence, machine learning, it has sort of been built up as we sort of, like in old computer games and stuff like that, that we have a world, we have the data for it, and then we give it the rules. And then it sort of gets the answers out of it. So like we have to specify, like if this character has a certain speed, if the speed is less than 4, then maybe it's walking. If it's higher than, if it's less than 12 but higher than 4, then it's running. And if it's more than 12, it is biking or bicycling or something like that. But this type of programming becomes very much like an expert system. We have to tell the computer what the rules are, what the thresholds are. And if we want to add another one, golfing, we can't really do it in this way because then we have to really redesign everything, code stuff for that. It becomes very static and cumbersome to do AI in this way. So what has happened with AI machine learning is that we have sort of flipped this a little bit. So modern machine learning is built on that we actually give it the data, but instead of giving it the rules, we are giving it the answers. So that we are giving it the data and the answers, and the machine learning sort of model and system has to figure out the rules itself. So instead of giving it the rules for walking, we just give it a lot of data where a person is walking, for example. And the same thing about running and biking, and then it can learn the rules itself to determine whether or not a person is doing what. And then we can just add another set of data for golfing, and it becomes also very dynamic in that sense. And this is the sort of the core of machine learning, that the machine learns the rules itself. And that is what sort of has happened in this domain now in the latest years, that we really have moved away from traditional programming of AI machine learning to this new way of doing it. So let's have a look at the tools then, the coding tools and stuff like that. Because as I said, a lot of things have happened there as well. The currently most popular tools for doing applied machine learning has really become a technology stack that consists of TensorFlow and Keras, and a system of Python notebooks. That's really become the technology stack for this. Really, sort of moved everything else out of the way, basically. So first of all, Python, as you probably know, Python is a programming language, and it has become like the de facto standard for data science. Really pushing away old things like MATLAB and stuff like that is really going down. Python is really the thing that everything is happening around right now. And the notebook style of Python has also become very good for machine learning. It has very many benefits for this. I mean, compared to the old script style, writing a script in a file and running it that. The new notebook style has more of because we can run different parts of the code very easily in different steps and stuff like that. And that fits very good when you are exploring the area of machine learning. Fits very well. And then we have the other two tools, TensorFlow. And TensorFlow is an open source machine learning AI software library, actually. And it was primarily created for doing deep neural networks, which we will talk a little bit more about. It was initially developed in 2015 by Google, and has since then really sort of taken over quite a lot of this domain. And one of the reasons why it became so good is actually Keras. So Keras is actually an open source software library as well that sort of extends TensorFlow. And what Keras did was that it provides a very easy to use Python API for TensorFlow, making it much easier to use the technology and making it really available and for anyone to sort of understand it and use it. And nowadays it's almost impossible to use TensorFlow without using Keras, because Keras is like fully integrated into TensorFlow today. But this is the technology stack that sort of everybody uses in this area these days. So how do you get started? And here a lot of things has also happened during the last years. There used to be a lot of problems installing Python, installing TensorFlow, Keras and stuff like this. There were a lot of versions you had to match and fix and everything had to be installed properly. But during the last years, Google has also launched their own sort of web version of this. So that is called Google Colab. And if you want to get into this area, I just suggest you start with that. Easiest way is just to go to Google Colab, log in with your Google account, and then you can start coding right away. Everything is installed in the way that it should be. All the versions are there. Everything works. You get the Python notebook style programming interface and everything. It's very easy to just get started. Of course, then the code is being run on like Google's clouds and stuff like that. And if you want to do a very big project, maybe you need to pay them and stuff like that. But that's for advanced users. But if you just want to get into the area, this is a very good place to start. Okay, I said I wasn't going to talk about mathematics, but we're going to talk some fundamentals at least. So let's look at the pipeline for machine learning. So when you're doing applied machine learning, there is sort of two phases that you're going through with all the code, and we're going to see this later in the code as well. So what you're doing is first you need to train your model, what is called your machine learning model. And you do that by having this set of data, the training data that you want it to learn on, the running, the walking, the biking, as you saw before. So you have the raw sensor values, the raw data that you want to use. And usually this data is not good in itself, because usually we need to do some data pre-processing. Maybe there's some missing data points, maybe there's some corrupt anomalies and stuff like that. Or maybe we just need to put it in an array in a good way so that the code can understand it. So there usually is some part of data pre-processing before you can make use of this. And then you need to select which type of model you will use, and then you need to train this model for some time on this data. And after you have done this, you then get your trained model out, and then you need to evaluate, was this model good enough, or do I need to train more, and stuff like that. And then you do this until you're satisfied with your model. And then you can take this model into sort of the inference phase, or like production. And then you just, instead of using training data, you take your runtime data, you apply the same data pre-processing so that the runtime data looks similar to the training data, and then you just push it into the training model, and then the model will spit out basically the predictions that you're after. So this is the pipeline that is used for applied machine learning. We are taking the training data, we are pre-processing it, we are selecting the model, training the model, and then when that is done, we can then use it in production with runtime data, apply the same data pre-processing, and then get the predictions out that we want. So let's look at the components of a machine learning model then. And this is very simplified, okay? So that you know, it's oversimplified maybe. So, the network, a neural network, which you have probably heard about, is it's sort of like the brain of the system. And this is usually illustrated in this way, as you see here on the screen. And then the parts of this is that we have the neurons, which can be seen as sort of the brain cells of this brain. So that we are programmed this model, the model is the brain. We have these blue circles, as you see here on the screen. Those are the sort of the brain cells of this model. And these sort of take input data and makes a trained guess out from themselves. And then we have layers, and that's basically the depth of the neural network. So in this picture here that you see, there are 3 layers in the neural network, and that sort of determines how complex patterns it can learn. And in this example, there is 3 layers, and usually there is an input layer that's like the first layer there furthest to the left, and then you have a number of hidden layers, and then you have an output layer. And this depth is also what defines sort of the deep neural network. That means just that it is a neural network that has many layers. So we have the input, we have a number of hidden layers, and we have an output layer, and it sort of determines how complex patterns this machine learning model can learn. Then we have a few mathematical functions that we don't really need to go into how they work, but we need to know what they do, right? So one thing that you will see in the code that comes up is activation function. So the activation function is a mathematical function that sort of decides which neurons has valuable results and which ones that hasn't. So we need to specify this in the code later. We will also see that there's something called the optimizer function, and the optimizer function is also a mathematical function that provides sort of guidance for the model in the learning process, basically choosing the next step to train, what is going to train next. And then thirdly, there's a third mathematical function that shows up in the code when we're looking at that, and that is called the loss function. And the loss function is also a mathematical function that is used by the optimizer function that basically calculates how far from the right answer we are. We can use this to determine if the training is becoming better and better, or what is happening with everything. So it's sort of the loss function helps the optimizer function. And we can choose different ones here, but we will see that later in the code as well. Okay, so let's have a look at the actual code then. So we're going to do a very simple problem. We're going to do a regression problem. And this is a very typical, simple mathematical problem. Of course, we can use other mathematical tools to do this. This is almost like hitting a very small nail with a very large hammer. But still, it really shows at least the basics for applied machine learning. So what we want to do is that we have this training data that you see here on the screen that goes there from -1 to up to 7 there. And then we want to sort of determine the trend, the curve of this for predicting the future. So giving these X and Y values, predict how the future follows, and also perhaps also how it was been before the training data. That's the task, okay? So the outline of the code is going to be like this. We're going to need to import some relevant libraries. We need to set up and load in the training data that we have. Then we will need to create the model and set all the parameters for it. And then, of course, we need to train the model and iterate that training until we are satisfied. And then we need to test it and see how well the training model performed, if it was good enough for us, for our production, or that we want to use it for. So that's the outline. Import training data, create the model, train the data, train the model, and then test it. All right. So how does this look in the code then? Well, first, of course, we need to import TensorFlow for all the machine learning functions that we need. And then we need to import NumPy, which is Python's sort of math library. And we basically mostly use it for the advanced arrays so that we can use arrays within it. And then we need to do the data pre-processing, right? We need to set up the training data in a good format so that TensorFlow can use it. And then we sort of create these two NumPy arrays that you see here down on the left here. That we will have basically an array of X values and an array of Y values that corresponds to the training data that you see in the graph. So you see here that we will have an array here of 5 values, 5 X values, and their corresponding 5 X values and their corresponding Y values here. So that at -1X, the Y should be -3, for example. And then we have our training data set up for TensorFlow to make use of. Then we need to perhaps do the more difficult part, and that is to actually create the model. And this is what we use Keras for. This is where Keras comes in and helps us with all of this. So in this example, we are going to do a very simple deep neural network. We're going to do 3 layers, as you see here, and we're going to do a sequential model, and that is something that looks like the picture you saw before, a very simple sequential model. So we're going to have an input layer, which is a fully connected dense layer, as the picture you saw before. And it's going to have 3 units in it, basically 3 neurons in the first layer. And then we also need to specify that it has an input dimension of 1, because every X value only has a single Y value. And then we need to specify an activation function. And in this simple example, we chose a linear as a very simple basic activation function. Then we create a hidden layer, which can be many, of course, but in this simple example, we have a single hidden layer consisting of 2 neurons, so that's the second layer here. And that also has a very simple linear activation function. And then finally, we have an output layer, that's the third layer here in the code, where we will have a single neuron, because we want to output a single value from this this AI model. We just wanted to spit out a y value. When we are giving it an x value, we just want an I value out. So the output layer is just one unit here that takes out the value we want. And also, like I said, linear activation for all of these, just to keep everything very, very simple. And then we need to make Keras compile everything and do this for us. And for Keras to compile it, we need to also specify the optimizer function. And for this simple example, we have just chosen a very basic stochastic gradient descent function for this. This is a mathematical function that is built in that we can just specify to use for it. And at the same time, we need to also provide the loss function for the optimizer. And here we use mean squared error as the most basic sort of loss function as well. After this, we train it. We just tell the TensorFlow to, okay, start training. And in this example, we maybe start by telling it to train it for 5 iterations using the training data x and y, the 2 arrays that we had. So we use model.fit, which is the training command for TensorFlow. And then we just give it the x values and the y values. And then we tell it to train for 5 epochs, basically 5 iterations through this. And of course, this is the step that takes time, right? If you have a really advanced model, a very deep model, very many neurons, and if you have a very advanced problem, this is going to take time to do the training. It's going to work on for quite a long time. But of course, this can be made quicker using better hardware. Maybe you can use your graphics card to train and stuff like that. But in this simple example, it's so easy, so this will go very fast. So there's no problem here. But if you have a harder problem, this is the step that takes time to execute. All right, so then after we have trained the model, we need to test it, see how well our model performs. So we only have had values from, what was it, -1 to 4. So now maybe we want to see how does it react if we wanted to predict from -3 to +6. So what we do then is that we create a new array of x values from -3 to 6 here. From -3 to 6. And then we tell our model to predict, basically. Use this test input, give me the y sort of array that corresponds to this, the y values that corresponds to this. And then after this, just for us to be able to visualize it, we can just plot the results using, for example, matplotlib in Python, just to plot it out, so we can have a good way of seeing how well our machine learning model performs. And this is sort of the resulting code there on the left, and then you see the output, the results on the right. So the left here, you see we have our imports first, and then we have the training data that we set up, then we have our model that we created, then we combine the model, and then we make it train for 5 epochs, and then we sort of test the output, and then we plot it out here. And then you see here on the right that this is, it's not perfect, right? But it sort of gets the idea a little bit. It tries to, so the green line you see in the figure here, that's the truth. That's the training data that we gave it. And the red dots here are the prediction that our machine learning model did. And we only ran it for 5 steps, and we see here that the first step took not even half a second to run, and each consequent step just took tens of milliseconds to run. So this was actually very fast to run. And we can also see our loss function here actually becoming lower and lower, so it is actually getting better and better for each run that we are running it. But of course, this can be improved. Perhaps just making it train 10 epochs will sort of improve this quite a lot. Then it be really sort of spot on, on everything. But this is just a very simple example. So that's the sort of the basic code for just doing a very simple machine learning sort of project. And if you're doing something more advanced, then you're just changing the training data, you're changing the model maybe to something what you want, making it train longer, use a different sort of optimizers and loss function and stuff like that. But the code structure and the pipeline sort of looks the same for this for all types of machine learning projects. So how can we improve it then? I mean, the process of sort of improving the model is what is called hyperparameter tuning. So, and that basically means testing different parameters in the code, sort of like having better, yeah, I mean, maybe making it train longer, as I said. If we just increase the number of epochs in my example here to 10, I think it will get very good results, for example. We can improve the neural network, both the depth, how many layers, and the width, how many neurons in each layer. So we can increase the layer size, add more layers, and see if we will get more better results. Of course, like I said before, a deeper network, a wider network makes it being able to learn more advanced patterns. So in this example, we just had a simple linear function, so it was very easy for it to detect. But maybe it's a much more difficult function. We can, of course, change the optimizer to other ones as well. ADAM is perhaps the most common one to start with. It's sort of one of the best for most general machine learning problems, for example. But there exist other ones as well that you can try. We can change the loss function to other mathematical functions, see if we can give it better. And then you can also change the activation functions and to different ones that exist. And these activation functions doesn't have to be the same for all layers either. Some layers may have different activation functions and stuff like that. So there's a lot of things we can do to increase, to improve this code and the model to solve this problem. And finally, I mean, the world of applied machine learning is actually so much more than just this, right? I mean, we know that we have seen, okay, applied machine learning in the domain of computer vision, natural language processing, sequence predictions. I mean, being able to do very, very advanced things. We have seen machine learning and AI be able to handle very large data sets, doing very advanced data pre-processing on everything, being able to extract which features to look at and stuff like that. This example that I showed you was also a typical example of supervised learning, but there also exists unsupervised learning, there exists reinforcement learning, transfer learning, so there exist many different ways here as well. What we saw here was a simple sequential neural network. There also exist convolutional neural networks, recurrent neural networks, many different variants there as well. There also exist a lot of optimization functions, as I said, dropout, self-attention, transformers, and stuff like that. So there's a lot of things that can be done with the model. There exist systems that is called generative adversarial networks that is used for these deep fakes, for example. Stable diffusion, which is used for generating these images from text that you maybe have seen. And then there's a lot also that deals with hardware acceleration, making machine learning run on smartphones, IoT devices. And there even exist topics such as AutoML, basically machine learning system that does the hyperparameter automatically for you, for example. So that this world is very large, and there's a lot of stuff is happening here in this domain right now. And it's hard to go through all of this because they're both very advanced mathematically and scientifically, right? But one thing that you should know and understand from this, that all of them sort of use the same basic tools. Almost all of these sort of use Python, TensorFlow, Keras. So if you really want to be good in this domain and want to sort of learn more and dig deeper, these are the tools to sort of be proficient with. If you want to become a good data scientist, AI, machine learning coder, developer, these are the tools that you need to be proficient with and learn more about. So with that, this was my very quick sort of crash course into this domain of applied machine learning. So if you have any questions, you can go into mentor.com and write those. You have the code here, and you should also see the code on the screen. And while you are writing your questions, I can just talk a little bit about this course that we also have. So we are running this applied machine learning course. This is maybe the 4th or 5th time we are running it. But basically, this lecture was sort of also the starting point of this course. It was the first lecture in this applied machine learning course that we have. And this is a very practical course. It's focused on Keras, Python, TensorFlow, and it's also made for working professionals. So it's made for people that maybe already have a job and working with it, And we just want to learn more about the domain on the side, and learn more, maybe able to take on new things at their work or something like that. So it's made for you. So it's very slow speed. It's 10 weeks, but not a lot of work. It's very flexible in format, with both the it's self-paced, and the labs you can do on your own time, and we have some scheduled tutoring, but we are very flexible when it comes to that. And it, of course, gives ECTS credits, HP. It awards 3 HP, so it's 3 HP over 10 weeks. It's on advanced level, and it's, of course, free of charge, as all university courses in Sweden are. And the next lecture actually starts in 2 weeks on Monday the 11th. So there's still time for you to apply, actually. So if you thought this was interesting and this okay, I want to learn more, you can actually apply for it right now and join us. And easiest to find this course is to apply or go to this website, www.mion.se/driven. And Driven is the project we have for these courses for working professionals. And on this webpage, you can find all the courses we are giving for working professionals in this format: flexible, slow speed, self-paced. And there you can also find this applied machine learning course, and you can click through there to get to the applications. But it can also be found on antagning.se if you want to go that way. You just need to search for basically hösten 2023 or the autumn 2023, and then you use the code MIU F2423 to find that particular course. It will look like it's because the regular time for applying for courses is over, so it will be like a late application. But if you apply now, you will get in. The prerequisites for reading this course, since it is on advanced level, we require that you have a bachelor's degree in computer engineering, computer science, electrical engineering, or something similar. And also that you have 15 credits of basic programming, so that you know how to code. We won't teach you how to code. Basic Python, we will, of course, look at Keras and TensorFlow. But if you have working experience and stuff like that, and maybe not the points on paper, you can contact us, and then maybe we can do some counting your working experience towards these prerequisites as well. All right. So let's see if we have some questions. If I have some questions, so let's see. The first question was, if I want to acquire hardware to use for AI coding and TensorFlow training, do you have any recommendations? Here, Monster GPU or maybe even multiple GPUs? I would say that get an NVIDIA GPU, because if you want to run it on your own machine at home, the drivers and stuff like that works best with NVIDIA. But there is a lot of drivers when doing this to get it to working. Well, you need to match the drivers on TensorFlow with the drivers, the version on TensorFlow with the version on Python with the version of the NVIDIA drivers correctly, so you set everything up correctly. But that is my suggestion. But if you just want to get started, you can get really far just using Google Colab. And if you need to do something bigger, you can just pay Google a little bit more to use their cloud a little bit faster as well. So you can value that against each other, what you should do. Yes, okay, so you want to do the supervised learning in image processing. Okay, yeah, but basically, like I said, the GPU speeds up the training process for you when doing this. So it's that's the purpose of using the graphics card. And you had a question there also regarding multiple graphics card. I don't think that is particularly necessary right now. It also makes it more complex to set up, to run it concurrently on many graphics cards at the same time. So getting one good is probably easiest thing to set up if the Google Colab stuff isn't enough for you. All right. Any other questions? For you, it seems like there maybe was some strangeness with the sound in the beginning. Hopefully you guys got most of it that I talked about. there was also a question regarding the schedule when the course starts, but I'm not exactly sure about the dates here right now. But basically, the course starts formally in 2 weeks. That's when the next lecture is. The course is already available, so if you apply now, you will get access to our course materials and everything. But the next real lecture starts in 2 weeks. And then we also got another question regarding the course. Yes, we will run this. We usually run this yearly. That's we have done for the last 4 or 5 years. One year we even ran it twice in 1 year. But usually now the latest years here we have run it 1 time per year, and it's always been now like directly after the summer. So it will run next year as well. All right. And then there are some people thanking me for my presentation. And I thank you all then for listening. And hopefully you got a good into this domain and got a good introduction. And hopefully you feel like you want to learn more in this domain of applied machine learning. All right. So with that, thanks for listening.